Okay, we'll start with the derivatives of exponential functions here. And we're working with the first function is e to the 2x. And let's just review for a second. The derivative of e to the x is e to the x. Now if we have function composition, the inside function is a function in the exponent. And so that would look like, we would say the derivative with respect to x of e to the u, where u is some function of x, as in this case it's 2x. And that would be, take the derivative of the outside, and the derivative of e to the whatever is e to the whatever, then times the derivative of the whatever with respect to x. And so let's get started on this particular one. So the derivative of e to the 2x starts off with just e to the 2x. And then we have to multiply that by the derivative of 2x. The derivative of 2x is just 2. And so we end up with 2e to the 2x. Okay, so the next problem, number 41, we could look at it a couple of different ways. The first thing that I want to point out is when you see an exponent with a sum in it, you want to recall that when we multiply two numbers with the same base, we add their exponents. So whenever you have exponents added, you have to remember that it also can be represented as a product of two numbers with the same base. In this case, it would be e to the negative 2x times e to the x squared. We could do that, and then we would have to take the derivative using a product rule. It may be easier just to do with a chain rule the way that we have been doing. So once again, all negative 2x plus x squared is some function of x. And so we really have e to the u, and so the derivative of e to the u is e to the u times du dx. So let's see what that looks like. Well, it just starts off as it is, e to the negative 2x plus x squared. Then we're going to multiply that by the derivative of negative 2x plus x squared, which is negative 2 plus 2x. And so we end up with 2x minus 2 times e to the negative 2x plus x squared. Now again, thinking ahead, which we're going to be doing not very soon after we complete this section, so we want to find out where that's 0. Well, you can see that'll be 0 whenever x is equal to 1/2. Now that's the first factor, will be 0 when x is 1/2. But the second factor, the exponential function is never 0. It never crosses the x-axis unless we subtracted or added something to the end of it, not in the exponent, but at the very end. So that piece will never be 0. That whole function, that whole derivative will only be 0 when x is equal to 1/2. And other than that, it's defined everywhere. Next problem, we have e to the square root of x, which can also be written as e to the x to the 1/2, which is kind of crazy, but we'll go ahead. Take the derivative of e to the x, always starts up. E to the u is e to the u, which is just, in this case, is e to the square root of x. Now we need to multiply that by the derivative of the square root of x. Square root of x is x to the 1/2, so we'll have 1/2 x to the negative 1/2. And if you recall, that comes out to be 1 over 2 times the square root of x. And so this problem just ends up being e to the square root of x over 2 times the square root of x. In the next problem, we're looking for the derivative of e to the negative t plus e to the t quantity cubed. You should see here that we have a chain rule. We have function composition. The outside function is something to the third power. So the first thing we're going to do is apply the power rule. And so that is 3 times whatever the inside function is raised to the second power. Now we need to multiply that by the derivative of the inside function. And the inside function is a sum, so we're going to have to take the derivative of each piece individually and add them together. So e to the negative t is just e to the negative t times the derivative of negative t, which is negative 1. Since originally we had a sum, we're going to add the derivative of e to the t with respect to t is just e to the t. And if I were to rewrite and place the positive term first in the second factor, I would get 3 times e to the negative t plus e to the t times e to the t minus e to the negative t. And I don't believe that we have any common factors in there, and we'd have to leave it that way. Okay, so that's the answer to that. Or maybe the book shows something more can be done there, but it's fine.